Welcome back. Most likely you've just worked your way through the improper integrals over infinite intervals, and the last thing you want to do after that is deal with another kind of improper integrals, but there is another kind of improper integral. Improper integrals over infinite intervals talk about things that have infinite width. Improper integrals across singularities, which is what we're going to talk about here, is talking about situations where you've got infinite height. And a lot of what we're going to see here is very similar to what we did in the previous presentation. And so here what I'd like us to do is I'd like us to look at the definition and realize that the spirit of the definition is very similar. We're going to establish that the computations are very similar. It's again limits of integrals. And we're going to talk about some estimates that we're going to use in the examples without really stating the theorems yet, because ultimately what you will get more long-term mileage out of is being able to work with the estimates and filling certain small computations in quickly, because memorizing theorems, especially as we're going to see theorems that work slightly differently, like the p-integral test for the two different kinds of improper integrals, that kind of memory decays over time, whereas your computational ability and your ability to work with inequalities will stay with you. Okay, first of all, why on earth would we want to figure out areas with infinite height? Well, we talked about the gamma function already, and then of course, well, why would you want to talk about the gamma function? But that's just an interpolation of the factorial function. For 0 smaller, alpha smaller than 1, the gamma function, which is defined via this integral from 0 to infinity x to the alpha minus 1 e to the negative x dx, that thing is defined with an integral that on the left boundary has a singularity, because when alpha is smaller than 1, then x to the alpha minus 1, of course, is x with a negative exponent, which means that blows up at 0, right? And so we need to see how we handle that, because apparently it is claimed that the gamma function is defined for alphas between 0 and 1. The other thing, and this is now something that is an application, is if we were to try to bring two charges, q1 and q2, into the same exact point in space from a distance of b, then the work that is needed would be the integral from one point to the other point over the force that is required times the little distance traveled, right? Work is the integral of force against the distance function, and the forces, the electromagnetic force, the electrostatic force, there is no magnetism in here, which is, as long as we're working with international units, q1 times q2 divided by 4 pi epsilon 0 times 1 over r squared, and I specifically wanted to write it like this because, of course, this thing here, even though it's big and ugly and everything, this is just a number that can come out of the integral. The hard part will be to figure out the integral of 1 over r squared, and we can find the antiderivative. The hard part is to figure out what happens at 0. So again, here also we encounter therefore an integral with a singularity on the left endpoint. Definition. Let's take a continuous function on an open interval from a to b, open on the right side, and so we're going to talk about singularities on the right end. Well, singularities on the left end are going to be very similar. If the interval from a to t of the function exists for every t in the interval from a to b, and if the limit as t goes to b from the left of all these integrals exists, then we define the improper integral from a to b to be the integral a to b f of x dx being the limit as t goes to b from the left, integral a to t f of x dx. So this definition is very similar to many other definitions in calculus. Is ultimately what we want to remember is this part, but what this part of course implicitly assumes is that these integrals exist in such a fashion that this limit can be evaluated. And so when that happens, the improper integral is called convergent. When this does not happen, then the improper integral is called divergent. So that is the same language as for the improper integrals over infinite intervals. And improper integrals with a singularity on the left boundary are defined the same way. That's where we would just let t go to a from the right and fix the b, right? So we would have integrals from t to b. And so this is part of what I said at the beginning. I want us to get to the point where we understand this so far that we can fill in little details such as saying, well, what do you do when the singularity is on the left endpoint? Well, there's only one thing to do. You approach the left endpoint from the right. when there are singularities inside the interval of integration, you just split the integral into improper integrals with singularities on the boundary. So just like when we had an integral from negative infinity to infinity, we split it at 0 or somewhere. If we now have an integral from a to b and there's a singularity in the middle, we would first go from a to c and then from c to b. And both of those improper integrals would have to exist. So there's a lot of stuff that you can write out that is potentially also written out in your calculus book. But I want to get us to the point where we can, with a clear conscience, say, of course that's what it is, and yes, I could have thought of that too. So let's just look at a straightforward example. Let's compute the improper integral from 0 to 2 of 1 over root 2 minus x dx. Well, does that work? As long as x is smaller than 2, 2 minus x is positive, so yeah, that is all defined. So let's see. Well, the integral is the limit as t goes to 2 from the left, integral 0 to t 2 minus x to the negative 1/2. And so then, of course, the antiderivative will be, let's see, negative 1/2 plus 1 is 1/2. 1 over 1/2 is 2. So I end up with a 2. Because of the substitution we have in here, we get an extra negative sign, so we get negative 2. And so it's just negative 2 times 2 minus x to the 1/2. Remember the reading skill I always recommend. Yes, I know you can do this with a u substitution. If you read it like this, just take the derivative and realize that the derivative turns out to be the integrand here. It's taken at the bounds 0 and t, which is the limit as t goes to 2 from the left, negative 2, 2 minus t to the 1/2 plus 2 times 2 to the 1/2. As t approaches 2, this goes to 0. So the integral is 2 times root 2, and that's it already. And if you want to visualize that, well, here is the function, and here's the area underneath the function. From 0 to 2, we can see that even though the height is technically infinite here, because we've got a vertical asymptote, we have a finite area. Okay, let's talk about the gamma function real quick. We want to show that it is defined for alpha between 0 and 1. Well, gamma of alpha is this integral from 0 to infinity, x to alpha minus 1 e to the negative x dx. We break that up into the integral from 0 to 1 plus the integral from 1 to infinity. We know that the integral from 1 to infinity has no problems. Because of the e to the minus x, this one is actually defined and finite for all values of alpha. This is the part that we have to worry about. And so on the interval from 0 to 1 for x, we have that x to the alpha minus 1 is less than or equal than x to the alpha minus 1 e to the minus x is less than or equal than x to the alpha minus 1, because e to the minus x is still greater or equal than e to the 0th, and e to the 0th is 1. So, now wait, e to the negative x is less than or equal than e to the 0th, and e to the 0th is 1. So e to the negative x is smaller than 1, so that this thing is smaller than x to the alpha minus 1. Well, for alpha between 0 and 1, we have that the integral from 0 to 1, x to the alpha minus 1 dx is 1 over alpha minus 1 plus 1, so 1 over alpha, x to the alpha minus 1 plus 1, x to the alpha, in the bounds t approaching 0 from above, and 1. And as long as alpha is between 0 and 1, this is a positive exponent, which means as t approaches 0, we get 0 at the lower bound, we get 1 at the upper bound, so that is 1 over alpha. So that means that the integral of x to the alpha minus 1 e to the negative x dx converges for alpha between 0 and 1. Basically, and here's what I've weaved in and what we're then going to talk about explicitly with the theorems, what we're using here is that the area we want to compute is less than or equal than an area that is finite. And if an area that we want to compute is less than or equal than an area that is finite, then it must be finite itself, which means that this integral must converge. So there is a comparison test that works just the same for improper integrals across singularities as for improper integrals that are over infinite intervals. And there also is a p-integral test, but this one I definitely wanted to do explicitly because for x between 0 and 1, your inequalities shift around, and we're going they're exactly the opposite as for x greater than 1, and we're going to see that also when we talk about these theorems here. Okay, so this integral converges for alpha between 0 and 1. There should be a less than or equal here. Well, and that's not a problem. Or, well, doesn't need to be. Alpha less than 1 is perfectly fine. Here is where I'm struggling between x and alpha, because they satisfy very similar inequalities, which is exactly a case of something that I would also tell you in class, which is you've got to make sure what applies to what variable, but the problem has several variables we have to keep track of. Okay, so that means because this integral converges for alpha between 0 and 1, the gamma function is defined for alpha between 0 and 1, because this integral works for all alpha, and this one now also works for alpha between 0 and 1. Now the visualization of that is that the gamma function, basically because these integrals for alpha between 0 and 1 over of x to the alpha minus 1 e to the negative x from 0 to 1 get bigger and bigger, the gamma function actually blows up here at the origin. And so it actually turns out that the gamma function is not defined for alpha greater than 0. And it's the same story, alpha less than or equal than 0. And it's a similar story because for alpha less than or equal than 0, we have that the x to the alpha minus 1 e to the negative x on the interval from 0 to 1 is so that e to the minus x is greater or equal than e to the minus 1. And x to the alpha minus 1. Now remember, these things here are fractions, right? These are numbers like 1/2, 1/4, and so on. And if you raise that to a negative power, which is what we would be doing here, then this is actually getting larger because we've got an extra 1 over here. This is getting larger the larger the negative number is, or the larger the absolute value of the negative number is, which means that x to the alpha minus 1 is actually greater or equal than x to the minus 1 here. That is the key here. And, well, and that's on the interval for x between 0 and 1. And what we do know is the interval from 0 to 1, x to the negative 1 dx. That's ln x absolute value for t going to 0 from above to 1. And that's infinity because as the t approaches 0, the logarithm goes to minus infinity, and the minus gives us a plus infinity. And so that means that these integrals must diverge for alpha less than or equal than 0 because they are greater than something that is already infinite. And so that means that the gamma function cannot be defined in this fashion, at least for alpha smaller or equal than 0. And because the gamma function blows up at the origin there anyway, there is at least no natural way in real analysis to extend the gamma function. I believe there is a way to do this in complex analysis, but that is an entirely different story where you may want to take a complex analysis course. All right, so we have an example how to compute an integral that cooperates. We have the gamma function, which shows that sometimes when the integrals don't cooperate, you have to do estimates. Let's also take a look at the other motivation we had, which is the energy that would be needed to put two charges into the same point in space. Well, the integral from 0 to 10 to the negative 10, which is about the radius of a hydrogen atom, well, of q1, q2 over 4 pi epsilon 0, 1 over r squared dr. Well, as I promised, the ugly constant comes out. It's just the integral of 1 over r squared. And the antiderivative of 1 over r squared is 1 over r, or 1 over t. Upper bound is 10 to the negative 10. T goes to 0. Well, as t goes to 0, this goes to infinity, right? And so that means here, thank goodness for quantum mechanical effects. Without quantum mechanical effects, electrons which are positively charged would fall into the atomic nuclei, which are electrons positively charged. Oh my goodness. Electrons are negatively charged, which would fall into atomic nuclei which are positively charged. And they would release, on that way of falling in, they would release potentially infinite amounts of energy. And that would not be good, because that would not be an energy source, because all this stuff would have collapsed a long time ago as the universe started stabilizing, and we would not exist. So thank goodness for quantum mechanical effects that keep that from happening. Without quantum mechanical effects, fusing nuclei also would be impossible, because it would take infinite energies, or near infinite energies, to get nuclei close enough together to fuse. And I mean, they just wouldn't fuse because they would repel each other. In that case, the sun would not exist because the sun derives its energy from nuclear fusion, and that would mean that we wouldn't be here. So again, thank goodness for quantum mechanical effects. Even though quantum mechanics is very, very difficult, it is a field that basically explains or gives us models about how this universe and how physics works. Yeah, let's see, where was I going with that? I just had a thought that straight fell out of my mind here. Yeah, the other thing is then an argument like this also in some ways shows that even if we didn't know quantum mechanics exist, definitely the first one would tell us there has to be another effect going because atoms are made up of electrons and nuclei and the electrons simply aren't falling in, even though they would, based on classical electrodynamics. So this is something that even in a time and age where classical physics was all that was available would tell us there's got to be something else going on here. And that's of course really cool because in some ways then electromagnetics is a theory that predicts its own limits and then says that there's got to be something beyond electromagnetics. Okay, now some theorems real quick, and I think it's a lot of graphics. The P integral test at a equals 0. Basically, you can compute these things, right? But if you want to say it, and we already did that, for P between 0 and 1, the improper integral from 0 to 1, 1 over x to the P dx converges. You could compute that. And basically, what happens is, wait a minute, that's wrong, I think. No, it's actually right, and that's exactly, teachable moment, it's exactly what I talked about earlier on. If you just try to remember those tests verbatim, at some point in time something will go wrong. You've got to understand those things. So what do we have here? We've got x to the minus p, right? And if we integrate that, we would add another 1. And if p is between 0 and 1, that means we would get a positive, or at least a non-negative exponent. And that means that the limit as x goes to 0 exists. So these integrals converge for p between 0 and 1. For p greater or equal than 1, the improper integral diverges. And if you compare that with the analogous theorem for integrals from 1 to infinity, convergence and divergence exactly have been switched. And so rather than proving this thing, which is something that you can do by yourself, and rather than talking about the way this is formulated, let's look at the picture. And really, the breaking point again is 1 over x. 1 over x basically is the bad guy. You can't integrate it from 1 to infinity. You can't integrate it from 0 to 1. It's got infinite area on either end. If we're looking at 1 over x to the p with p greater than 1, well, for going to infinity, 1 over x to the p is below the bad guy, and it turns out, because that's the breaking point, that these integrals as from 1 to infinity converge. However, for p greater than 1, the integrals here, the function is above 1 over x, right? Because what we're doing here is we are taking a number, a fraction like 1/2, we flip it, we get 2, and then we raise it to a number bigger than 1, so that makes it even bigger. And so that means that this blue area here contains an infinite area, and that means this blue area under the blue function cannot be finite. And similarly, 1 over x to the p, well, that's where we knew that for p smaller than 1, from 1 to infinity, the integrals diverge, and that's because they contain an infinite area. But because for p smaller than 1, we're taking roots here essentially, and taking roots of these large numbers we're getting here just makes the area smaller. It turns out that these areas actually are finite. If you want to have a symbolic way to work that out, go ahead and just solve the integrals. It's not that hard. In fact, with p being replaced by alpha or by alpha minus 1, we already did that for the gamma function. All right, the other thing that we have is the comparison test. Basically, the story for the comparison test is always the same. If you have an area that is supposed to be finite, like the area under F, if you then have an area that is inside that finite area, like this area under G, then if this area is finite, this area must be finite too. Or if the area under G is infinite, then the area under F must be infinite also. So the theorem just says that. And it basically works the same way for the integrals involving singularities. We've just seen it with the picture. Take a smaller b, take f and g to be continuous functions on the half open interval. so that f is greater or equal than g is greater or equal than 0 for x between a and b. If the integral of f converges, if the larger area is finite, then the integral of g converges, then the smaller area is finite also. Equivalently, if the integral over g diverges, so if the area that is trapped by g is infinite, then the area under f must also be infinite, so then the integral of f must diverge also. And if we want to revisualize that, here's the picture. The comparison test will not apply if the larger area is infinite, because if the improper integral of f diverges, well, then I know that this big area is infinite, but the area under g is smaller, and something that is smaller than infinity, or smaller or equal than infinity, could be infinite or finite. Any area is smaller than an infinite area. And the comparison test does not apply if the integral of g converges, because if the smaller area is finite, well, an area that is larger than a given finite area can be finite or infinite. Okay, that's it. This was hopefully short and sweet for you, because the ideas really aren't that bad if we piece everything together. Now, I know full well that especially as you are taking calculus, and believe me, I had my challenges there also, especially as you're taking calculus, it is still really hard to take those pieces out of your memory and put them together in new ways. But as you move on, and this is again near the end of single variable calculus, as you move on to multivariable calculus and various other things, this skill of piecing things together from stuff that you know will become more and more valuable, because the number of details will only increase. The number of details will only get worse. That should not discourage us, because it can be done, but the less we are intimidated by the number of details, the more we realize, yes, I can piece that together. And if you can shoot yourself through these kinds of computations, it's another indication you can. The more we can do that, the less of a challenge these more complicated scenarios will hold for us, and that's of course the ultimate goal. So take a look at the homework. You may have to mess with the comparison test a little bit. You may even want to read up on it and see some examples, but I leave that up to you, because I really want you to push your mind here in the direction of deriving things for yourself. All right, enjoy, and I think I'm gonna have lunch.